This method of that analysis of indeterminate structure, the subject name. In that stiffness matrix method, the module 5 will be discussing. Today we discuss the session 1. What is the outcome of this course is construct the bending moment for beams and frames. That the contents, introduction, method of approach, steps in stiffness matrix method, then MCQs, that is multiple choice questions. In that introduction, what is stiffness matrix method? Means in that displacement components of various joint will be determined by knowing the basic unknowns. We call it as that is stiffness matrix method. First, we identify the degree of kinematic indeterminacy in a member. In that, we already discussed in flexibility matrix method how to identify the kinematic indeterminacy. Then, what is the stiffness equation we form to solve the stiffness matrix? That is, member in a force will be determined by this stiffness equation, that is delta is equal to K inverse, that is of P minus Pn, that is delta is equal to, what is that one? Displacement. K is the stiffness matrix method, then P is the force, then PL is equal to force development in each member. The steps followed in stiffness matrix method by structural approach are: first one is determine the degree of kinematic indeterminacy. Second one is determine the coordinate members to unknown displacement. To know the unknown displacement, we can assign the coordinate for that particular member. Then impose restraints in all coordinate direction to get a fully restrained structure. How to get the restrained coordinates we discuss in a problems directly. Then fourth step is determine the force developed in each of the coordinate directions of a fully restrained structure. It is called as PL. That is the 4 steps. Then determine the stiffness matrix, that is K, by giving unit displacement to the restrained structure in each of the coordinate direction, and find the forces developed in all the coordinate directions. The sixth one is observing the final forces in various coordinate directions. Note the final forces, that is P. Then that is 7th step is solve the stiffness equation. What is stiffness equation? We discussed in our first steps, that is delta is equal to K inverse of P minus PL to get displacement in the coordinate direction. 8th one is that is calculate the member forces using this joint displacement. This is the 8th step. Then we know how to solve the problems, that is analyze the continuous beam shown in a figure 1 by stiffness matrix method. Draw BMD, that is bending moment diagram. Then here the span content A, B, C. In that AB, that is uniformly distributed load of 60 kilonewton per meter. Then BC, that is 100 kilonewton. Okay, that is AB is equal to, that is 4 meter span. This is 1.5 meter, here 1.5 meter, that is in a problem. Solution: number of unknown displacement is equal to 2, that is theta B and theta C. These are the 2 unknown, that is kinematic indeterminacy. The above beam is 2 degrees of kinematic indeterminacy. What are the kinematic indeterminacy means? Theta B and theta C. This joint, theta B and theta C are these 2 kinematic unknown displacement. We can find out theta B and theta C here. The coordinate selected and the fully restrained structure as shown in a below figure, that is this figure, that is ABC, in that we are applying the unit load at 1, unit load at 2, that is B and C respectively. For that is fixed end moment for a span AB and BC, we can that one MFAB, that is UDL, that is WL square by 12, here that is minus 80 kilonewton per meter. MFAB is equal to plus 80 kilonewton per meter. Similarly for BC, that is uniformly concentrated load acting at a center, that is MFBC is equal to minus MFCB, that is minus of WL by 8, that is equal to minus 37.5 kilonewton meter. Okay, that is WL by 8. The forces, that is movement in the space developed in the coordinate directions due to the given loads are P1L is equal to, that is you see this one 80, that is MFBA minus of 37.5, that gives how much, that is 42.5 kilonewton meter. Then similarly for P2L is equal to MFCB, here CB, that is how much, 37.5 kilonewton, this joint and this joint. How to get this one means MFBA plus MFBC is equal to 0. Here MFCB is equal to 0. MFCA is equal to, that is 37.5. Then the stiffness matrix, we can find out how to find out the stiffness matrix, that is K value, how to generate that K value. It is assembled using the slope deflection equation, that is same as your slope deflection equation. Unit displacement in the coordinate direction 1, you are applying the displacement at coordinate 1, that is B, that is K11, here K21, that is C. 1 radian rotation is given to support B in coordinate direction 1. The forces developed in the coordinate direction 1 and 2 are found, that is 1 and 2 are found. Then K11 is equal to, that is you see this one, this is the slope deflection equation, same as your that is 2 EI by 4 theta A plus 2 theta B minus delta is equal to 0, therefore 3 delta by L is equal to 0 here. Similarly plus 2 EI by 3 into 2 theta B plus theta C minus 0. This is your K1 value. Here we find out the theta B and theta C value. You see this one K11 is equal to, you see this one Ka is equal to 0, theta B is equal to 0, and theta B is equal to, you are applying the theta B is equal to 1. Okay. Here theta K11 is equal to how much we are getting, you substituting here theta A and theta B value here. Okay, theta B is equal to 1. You substitute theta B is equal to 1, theta A is equal to 0, and theta C is equal to 0. We can get this value. How much that value? That is 7 EI by L. Okay, if any confusion, please ask me here. Here theta B is equal to 1. Here theta C and theta A. Here we are doing mistake here. Theta B is equal to 0 here. Okay. Then similarly you generate the K21 is equal to 2 EI by 3 of theta B plus theta 2 theta C is minus 0. Here theta A is equal to 0, theta B is equal to 0, theta C is equal to, theta B is equal to 1. Here we are applying these two equations. This is 0, this is 1. Okay. Therefore 1 into 2 EI by 3 is equal to 2 EI by 3. We are getting this value. Then displacement in the direction 2, you are applying the displacement at 1. Here theta is equal to 1. K21 is equal to 2 EI by 3, that is of 2 theta B plus theta C minus 0. Okay. We are getting that value. You are substituting theta B is equal to 1, theta C is equal to 1 here. You see this one? Theta C is equal to 1, theta B is equal to 0, and theta A is equal to 0. Then K21 is equal to 2 EI by 3, that is we are getting this value, this into this 1, we are getting this value. Then K22 is equal to 2ei by 3, theta b is equal to 1. We substitute theta b is equal to 1. Here theta c is equal to 1. Okay. Then final force acting in coordinate direction at 1 and 2 are 0. Therefore, P is equal to 0. Here also 0. Then K is equal to, you know that K11, K12, K21 and K22. You will see this one, this value will be substituted for this matrix form. We are getting K is equal to EI of 7 by 3, here 2 by 3 and 2 by 3 and 4 by 3. Then K inverse is equal to 3 by EI divided by 1 by of 7 into 4 minus 3 into 2. This is the inverse of process. We are making the inverse process of K inverse. Then 4 minus 2. This interchanging this value, and here sign value will be changing here. Okay. Here interchanging this value and changing this value. We are getting this is the K inverse matrix. To substitute, we know that a stiffness matrix equation, that is delta is equal to K inverse of P minus PL. Here know this P is equal to 0. We are know that P is equal to 0 here. To substitute this value for this is 0. We are making this delta inverse. We are intention to find out the delta. That is capital delta is the theta B and theta C are the unknown. We know that theta C and theta B value is equal to, we are inverse of 3ei by 1 by 4x, 4 into x, 4 into 7 minus 2 into 2. In that 4 minus 2 7. That is 0 minus of minus 42.5, here minus 37.5. Here theta B, theta C is equal to 1 by EI, that is minus 11.875, here minus 22.188. Here theta A is equal to 0 since it is fixed end. Therefore, theta A is equal to 0. We are getting theta B and theta C value is equal to minus 11.875 EI, here minus 22.188 EI. In that theta is equal to 0, if final end moment EI is equal to constant or equal to 1 means you can get that value. The final end moment is equal to MFAB is equal to MFAB plus 2EI by theta A plus 2 theta B. Like that we can substitute this value for fixed end moment for MAB, that is minus 85.938 kilonewton. We are getting this value. You see this one, you substituting for this value. Okay. That equation will be substituted for this value. We are getting that value. Then MFBA is equal to, that is 80 plus 2A by 2 theta B. That gives 68.130 kilonewton. Then third one is MBC is equal to minus 37.5 plus 2EI by 3 of minus 2 into 11.875 by EI minus 22.188 by EI. That is, we are getting minus 68.130 kilonewton. Then MCB is equal to 37.5 plus 2EI by 3 of minus 11.875 by EI minus 2 into 22.188 by EI. That is equal to 0. That is MCB is equal to 0. That is for injured support. Okay, this is same as your slope deflection equation. We substituting theta value in each equation, we are getting this value. Then we can find out that bending moment diagram, that is parabolic, that is WL by 8, that is 120 kilonewton meter. Here WL by 4, we are getting that 75 kilonewton meter. Okay, that is MAB is equal to how much? That value 85.935. This is minus, this is plus, this is plus, this is minus, this is minus, this is plus, this is minus, this is plus. Like that we can see this one minus 80 5.938 is equal to, that's upward. Here 68.130 kilonewton meter, this is upward. Then that is C is equal to 0, that is here. Okay, that value is 0. This is the pattern of bending moment diagram for a member. Okay, if any doubt in the bending, this is parabola. Okay, this is parabola. We can see that one. Then coming to the multiple choice questions, that is matrix method. That is stiffness matrix is always, okay, we can say that is symmetry, non-symmetry, anti-symmetric, depends upon the load applied. Here, always stiffness matrix or symmetry, whatever it may be, that will be always symmetrical. That value, that is answer is A, that is symmetric. Then coming to the second question, for computational purpose, deflected primary structure, actually structure should be, that is as different as possible, as similar as possible, it does not matter in between. ಏನಾಗಿರ್ಬೇಕು ನಿಮ್ಮ ಕಂಪ್ಯೂಟೇಷನ್ ಡಿಫ್ಲೆಕ್ಟೆಡ್ ಪ್ರೈಮರಿ ಸ್ಟ್ರಕ್ಚರ್ಸ್ ಹಾಕ್ಬೇಕಾದ್ರೆ that value is always ಏನಾಗಿರ್ಬೇಕು ಸಿಮಿಲರ್ ಆಗಿರಬೇಕು. We can find out easily for solution for that value. Then indeterminate structure of a symmetrical structure is difficult from that of a non-symmetrical one. State whether the above statement is true or false. Okay, true or false, we see this one, indeterminate analysis of symmetrical structure is difficult. Okay, symmetrical idre ಏನಾಗುತ್ತೆ ಅದು easy ಆಗುತ್ತೆ, but your statement is false, that is. Then fourth one, normally which of the following things may or may not be symmetric to develop symmetricity? That is material, geometry, loading, and DKI, that is degree of kinematic indeterminacy. Normally that will be the answer is D, that is DKI, that is degree of kinematic indeterminacy. Then coming to the next part, that is how many compatibility equations should be written if we have n number of redundant reactions. N number of redundant reaction idre ಎಷ್ಟು equations ಬೇಕು ನಿಮಗೆ? Same number of equations ಬೇಕು, that is n minus 1 ಬೇಕಾ, that is n, that is r n plus 1 or n plus 2. Your answer should be ಏನಾಗಿರಬೇಕು, ಎಷ್ಟು ನಿಮಗೆ redundant reactions ಇರಬೇಕು, that much should be the redundant reactions. Therefore your answer is B. Okay, next, these are the some references, books we are referred for this content. That is thank you for listening this session.